Hello and welcome to the logic of it all. In this video, we are going to talk about the complement of a set and the difference between two sets. Let's start with the difference. So we have two sets A and B, and their difference, A minus B, which in some textbooks is written like this, and some other places like this, is going to be a set that contains everything that is in A but not in B. So that's the definition of the difference between two sets A and B. So for example, if A is 1, 2, 3, 4, 5 and B is 1, 4, and 8, their difference is going to be something like this. And if you have done this before, you can just look at these two sets and compute their difference. But if this is your first time, I recommend this way for doing the difference. So first you write down all the elements of the set on the left, in this case A. So write them all down, 1, 2, 3, 4, and 5. Then go through them one by one and remove the ones, delete the ones that belong to the second set, which happens to be B in this case. Okay, because they're not supposed to be in B. So is 1 in B? Yes, so delete it. Is 2 in B? No, so we're going to keep it. Is 3 in B? No, so we're going to keep 3 as well. 4 is in B, so 4 will be removed. 5 is not in B, 5 is not in B, so we are going to keep it. So 2, 3, 5 will be the difference between A and B, or A minus B. On the other hand, we can also do B minus A. So following the same logic, first we write down all the elements of the set on the left, which is B now. So write down all of them, 1, 4, and 8. Then go through the list one by one. If any of them belongs to the second set, which is A, remove it. So does 1 belong to A? Yes, so it's going to be removed. Does 4 belong to A? Yes, it's going to be removed. Does 8 belong to A? No, so 8 stays. And that's B minus A. Now immediately you see that unlike intersection and union, the difference between two sets is not commutative, which means that A minus B is not equal to B minus A necessarily. Okay? If some special cases, for example, if A and B are the same set, then A minus B and B minus A are equal because they're both empty. But in general, they're not equal. If you remember from previous videos, we saw that A intersection B is equal to B intersection A, and similarly for union. But for the difference, we don't have that property. In terms of the Venn diagram, for A minus B, if you see, we need to consider everything that is inside of A, so all this area in the circle, in the circle that represents A, and then exclude the parts that are in B, which is this part in the middle. And that's why the shaded area on the left-hand side represents A minus B. Everywhere that is inside A, but doesn't fall inside the circle representing B. Now for intersection and union, we did some special cases. Now one special case is if the two sets are disjoint, if they don't have any intersection, right? So if A and B are disjoint, their intersection is empty. Okay, and how would be the Venn diagram for A minus B in this case? So we need to shade every area that is inside A. So that's all this area, red area. Now we need to exclude every area that falls inside B, but nothing here needs to be excluded because A and B are disjoint. So that will be A minus B. So in this case, basically A minus B will be the same as A. And the other case is where one of the sets is a subset of the other. Now, let's consider the case where B is a subset of A. So A is this set here, and B falls inside of A. Now for A minus B, I need to include every area that is in A, but not in B. So it will be everything around B. So it's kind of like a donut shape around B. So this is the case where if B is a subset of A, then A minus B in the Venn diagram looks like this. Now, here's an example for you. We have the sets A, B, and C, and we are asked to compute A minus B union C. So again, similar to previous videos, I encourage you to pause here, do it yourself, and then check your answer with me. Now, I always tell my students to do these kind of things step by step. So just follow the definitions, keep calm and follow the definitions step by step. So let's do the union first, B union C. Okay, if you remember, that's not a prime, that's just C. If you remember, for the union, we write down all the elements of the first set, followed by all the elements of the second set, and if there are repetitions, we don't include them again. So that's B union C. Now we need to compute the difference between A and this set that we just calculated. So for the difference, if you remember, what we do is we first write down all the elements of the set on the left. So write down everything that is in A. So 2, 4, 1, and 7. And then go through the list, and for each one of them, if they belong to the second set, remove them. So does 2 belong to B union C? No, so we are going to keep it. Does 4 belong to B union C? Yes, it does. It's right here, so we are going to remove it. How about 1? Does 1 belong to the union of B and C? Yes, it does, so we are going to remove that as well. How about 7? Does 7 belong to B union C? No, it doesn't, so we are going to keep that, and as a result, the final answer will be the set containing 2 and 7. Now let's move on to the complement of a set. So we have a set A, its complement, which sometimes denoted as A prime, sometimes AC for A complement, is the set that contains everything in the universal set that is not in A. So everything that is in U but not in A. Another way of thinking of this as A prime is basically U minus A, everything in U that is not in A. Here U represents the universal set, if you remember. So here's an example. My universal set is the set of all positive integers less than 16. So that's 1, 2, 3, 4 up to 15. And then A is 2, 4, 6, 8, 10, 12, and 14. So all the even numbers. The complement of A will be all the odd numbers less than 16. So 1, 3, 5, 7, 9, 11, 13, and 15. In terms of the Venn diagram, so we need to consider everything that is inside the universal set, so inside the rectangle, but doesn't fall inside of A. So that's why you see that the shaded area is everything except the circle representing A. So that's the Venn diagram for A prime. Now, special cases, we always consider special cases for these as well. So if A is the entire universal set, then its complement is going to be empty because everything is in A, so things that are not in A don't exist. And on the other hand, if A is the empty set, then its complement is going to be everything. The set, its complement is going to be the universal set. Now, in this example, our universal set is the integers from 1 to 10. A is 2, 4, 6, and 8, and B is 2 and 7. So if you want to do the complement of A, that would be everything in the universal set except 2, 4, 6, and 8. So that is 1, 3, 5, 7, 9, and 10. So that's the complement of A. Complement of B, everything in the universal set, 1, 2, 3, 4 up to 10, except 2 and 7. So 1, 3, 4, 5, 6, 8, 9, and 10 is the complement of B. Now, if you want the complement of A union B, so A union B prime, again, if you remember, do this step by step. Just follow the definition. So first, ignore the complement, just compute the union. What is A union B? Write down everything that is in A, so 2, 4, 6, and 8, followed by everything in B. 2 is already there, so we don't write that again. So just 2, 4, 6, 8, and 7. Now its complement will be everything in the universal set, 1, 2, 3, 4 up to 10, except 2, 4, 6, 8, and 7. So that will be 1, 3, 5, 6 should not be included in the complement. 7, 8 will not be included, 9 and 10. So everything from 1 to 10 except 2, 4, 6, 8, and 7. So that's A union B prime. Now, on the other hand, if we do A prime intersection B prime, so the intersection of these two, if you check what's common between A prime and B prime, we have 1, 3, 5, 9, and 10. Okay, now you see that these two sets are the same. If we take the union and then take the complement of the union, or take the complement of A and B separately, and instead of union we take the intersection, we always get the same answer at the end. And this is not a coincidence. This is not for these specific sets. This is always true. This is an identity. It's one of the two rules that are called De Morgan laws. And in later videos, we will talk about that. But the identity looks something like this. For any two sets A and B, A union B prime is equal to A prime intersection B prime. So we distribute the complement between the two and change the union to intersection. Now, on the other hand, let me make some space here. On the other hand, we can do A intersection B prime. Let's do that. Okay, so again, step by step, first we do A intersection B. So what is the intersection of A and B? What's common between A and B? So they have 2 in common, and that's the only thing that they have in common. So its complement will be everything in the universal set, everything from 1 to 10 except 2. So it will be 1, 3, 4, 5, 6, 7, 8, 9, and 10. As you can see here. Now, if we take the union of A prime and B prime, which we have computed here, A prime and B prime, you'll see that the union of these two is going to be 1, 3, 4, 5, 6, 7, 8, 9, and 10. Again, these two sets happen to be equal. And that's not a coincidence again. That's the second part of the De Morgan's law that says if you want to take the complement of an intersection, you take the complement of two sets separately, change the intersection to the union. That's another set identity. So the equality between these two and the equality between these two, these are called De Morgan laws for sets. And as I said, in later videos, we will look into these in more detail.